In this video, we're going to look at a couple problems on 4.3 Part 1 homework. This first problem is asking us to use the first derivative test to locate critical points, and then from there classify those critical points as being local maximums or minimums, and then identify the absolute maximum or minimum. So the first thing we want to look at here is our function is only defined on -8 to 8. So we have endpoints to test as well. For Part C, you're going to test the endpoints to then verify if they are maximums or minimums. So the critical points of the function are going to be where the first derivative equals 0. Or is undefined. In this case, the endpoints at -8 and 8 are the value of the function is 0. So we're going to take the derivative and set it equal to 0. The derivative of this function is the product rule. Take the derivative of the first function, hold the second one, plus the derivative of the second function, this guy's 1/2 64 minus x squared times minus 2x. Hold the second function, or the first function. And we're going to set that equal to 0. Cleaning this up a little bit, we have the square root of 64 minus x squared plus, so this would be minus x squared divided by the square root, that's going to be to minus 1/2 power, 64 minus x squared. Set that equal to 0. So here we want to take a note that f prime of x does not exist when x equals plus or minus 8. So it's going to also be critical point is when the derivative of the function doesn't exist. But if I manipulate this and I add this term to the right side, I have the square root of 64 minus x squared equals x squared over the square root of 64 minus x squared. Now, the way this is set up, looking at the domain, the left side is positive and the right side is positive. So if I know they're two positive functions, I can square both sides and they still be equal to each other. So I have the 64 minus x squared equals x to the 4th divided by 64 minus x squared. Now if I multiply both sides by 64 minus x squared, I'm left with 64 minus x squared squared equals x to the 4th. Again, I know both these sides are positive, so I can take the square root of both sides, and in this case, the plus or minus the square root of both sides. So I have 64 minus x squared equals x squared. I add x squared to both sides. I'm left with 64 equals 2x squared. I divide both sides by 2. I have x squared equals 32. Which would x would give me plus or minus 4 the square root of 2. So that's going to be my critical points. So if I evaluate the first derivative of -8 minus 4 square root of 2, 4 square root of 2, and 8. If I plug in values into my derivative, so this is my derivative function, let's say I plug in 0. So if I plug in 0, the value of the function is the square root of 64, which is positive, minus 0, because I have a 0 in the numerator. So square root of 64 is positive. So that tells me from minus 4 square root of 2 to 4 square root of 2, the value of the derivative in that interval is positive. If I plug in a number greater than 4 the square root of 2, so let's say I plug in 6. If I plug in square root of 64 minus x squared, if I evaluate that at x equals 6, I get negative. So here, if I plug in minus 6, I get a negative number. So I get the value of the function doesn't exist on the left of 8 or the right of the left of -8 or the right of 8 there. So here are going to be my critical points. The slope is going negative, positive, negative. So this is going to be a local minimum, and this is going to be a local maximum. Local minimum, local maximum. Then you need to test the value of the function at -8, the value of the function at -4 square root of 2, the value of the function at 4 square root of 2, and the value of the function at 8 to test to see the global or the absolute maximum and minimum values. So this approach is getting closer to being able to graph this function using calculus techniques. So I can find the maximum and the minimum on this interval using the first derivative test. This next question is, a theorem states if a function is continuous on an interval and contains one local extremum, that local extremum occurs at C, then the value of the function at C is the absolute minimum on F. And if a local maximum occurs at C, then the value of the function at C is the local maximum. Verify the following function satisfies the condition of this theorem on its domain, then find the location of the absolute extremum guaranteed by the theorem. So in this case, this function is continuous everywhere. So on I, if we find a critical point, and there's only one critical point, we can conclude that critical point is the absolute maximum or the absolute minimum of that function. So let's see what's going on here. The function, we need to find the derivative. The value of the function, we need to find the derivative and set that equal to 0. So in this case, you're going to be careful because there's quite a bit of negatives going on here. So if I take the derivative, of the first function, I have -1, hold the second one, e to the minus x over 2, plus minus x, holding the first function, the derivative of the second function is e to the minus x over 2 times minus 1/2. And we're going to set that equal to 0. So I have minus e to the minus x over 2 minus a minus 1/2, so it's going to be plus 1/2 x e to the minus x over 2, set that equal to 0. I can factor out an e to the minus x over 2, that never equals 0, so e to the minus x over 2, I'm left with a minus 1 plus 1/2 x, set that equal to 0. E to the minus x over 2 never equals 0, so when does minus 1 plus 1/2 x equal 0? Well, that's when 1/2 x equals 1, and that's when x equals 2. So this is my only critical point. If I look at the first derivative test, and I'm looking at x equals 2, if I go back to this expression, e to the minus x over 2 is always positive. So if I plug in 0, I get a negative, right? If I plug in 0 here, then this is e to the 0, which is 1. This is minus 1, so that's negative. If I plug in x to be larger than 2, then the whole thing is positive. So my slope is negative on this side and positive on this side. So this tells me this is a local minimum. So it has an extremum of, this is my critical point, so if I plug that into the function, it's going to give me the value, and then that's going to be at x equals 2. So hopefully that kind of clears up what's going on there. If you have any other questions, please let me know.